Okay, let's look at section 10.4, still continued. All right, so let's try to prove this following theorem. All right, so it says that the cardinality of A is strictly less than the cardinality of its own power set. All right, so let's try to prove that. All right, first let's do the trivial case. What would happen if A happens to be in an empty set? All right, then let's look at cardinality of an empty set. All right, since there's nothing in it, so cardinality should be 0. Right, power set of empty set would be, what kind of set is that? It's going to be a set. All right, it has to be an empty set. So you have a set with an empty set in it, right? So since there's one element in there, so the cardinality should be 1, right? So from these two results, we can conclude that the cardinality of an empty set, which is 0, is strictly less than the cardinality of its own power set, right? So this one checks out, right? So from now we just assume here. So now we can assume that A is going to be a non-empty set, right? So let's do that. So assuming that A is non-empty, and we have to show a couple of things. And the first is that going straight to strict inequality is difficult. We're going to try to do inequality with equality, so less than or equal to. So we just need to come up with a one-to-one function from A to its power set. All right, so it's probably good to look at a small example to get some idea. All right, let's say A is a finite set and 1, 2, and 3 in it. All right, then I already wrote its power set, listed the elements of power sets. All right, then most natural way to get a one-to-one function would be maybe sending 1 to a set with only 1 in it, and 2 to a set with 2 in it, right? And the 3 to the set of 3 in it, right? That would be a one-to-one function, right? So that's the idea. So let's try to prove this guy. All right, so first thing we do is line number 1, all right? So we have to come up with the function. So we're gonna define a function f from set A to its power set by, all right, so we have take any element, send it to the set with that element in it, right? So this is just a definition, so I'll just say, right, this is just a definition of a function. All right, now we have to show that this is actually one-to-one, and it looks like it, all right, but we have to prove it. All right, so line number 2. All right, we're gonna have to start with, let's assume that the f of A1 is equal to f of A2. Then we need to show, so this is a given. Right, then all we need to do is show that the A1 is equal to A2, which is actually quite simple. Right, so next line would be 3. Right, so by definition of the function, f of A1 is a set with A1 in it, just A1 in it, and f of A2 would be the set with A2 in it, right? So this is using the definition from line 1, and of course using the fact that the A1 is equal to f of A1 is equal to f of A2. So I'm using line 2. All right, but for when you have a set D, in order for these two sets to be the same, we have to make sure that the elements in there are the same. So it means that the A1 must be the same as A2, right? So that comes from line number 3, right? Right, therefore, so this implies that say 5, right? Now we know that the F is 1 to 1. F is 1 to 1. Since line number 2 implies line number 4. Right? So conclusion number 6. Right? Therefore, we could find the 1-to-1 function from A to its power set. We know that the set A, coordinate of set A, is less than or equal to the coordinate of power set of A. Right? So this is that. All right. The next step would be, so we want a strict inequality, so that we have to show that there is no equality. All right. So 2. We need to show that coordinate of A is not equal to the coordinate of the power set of A. Right, so let's do that. All right, so let's write the argument. So I'm gonna move up here so that we have more room. All right, so we need to prove that there is no bijective function from A to its power set. All right, so let's prove it by contradiction. All right, so let's assume, so line number 1. All right, we're gonna just assume, for the sake of argument, assume that assume is the opposite of our conclusion. Let's say coordinate of A, all right, is actually equal to the coordinate of power set of A. All right, so this is just this assumption. All right, then we try to get a contradiction out of this. All right, so what can we say about this? So 2. All right, so if they are numerically equivalent, so there exists a function f from A to power set of A, right? That is 1 to 1 and onto at the same time. So it's a bijective function, right? So this comes from line number 1. All right. Then what we're gonna do is we want to show that we want to try to get we were trying to get a contradiction. So the way to do that would be, we're gonna find a set which is in this codomain, the power set of A, such that there's no corresponding element. All right. So 3. Right, we're going to define this set. So we're going to say define this set S to be, all right, so this is going to be a collection of elements in A such that, all right, X is not in the image of itself under the function. Right? Right. Remember this is going to be a subset of A, so it's going to be an element of the power set of A. All right. So this is just a definition. All right. Then what we're going to do is we're going to show that there is no element in A which is mapped to this particular set S. All right. So let's do that. All right, so it's 4. So we are trying to say that the F is not onto. All right, but it's supposed to be onto because it's a bijection. All right, so let's say, so since it's f is onto, there must be some element in A such that f of that element is going to be mapped to this particular set S. Right, so this comes from line 2 because f is onto. We know that the such y exists. All right, then we can say some strange things. We're going to look at a couple cases. All right, so case 1, what would happen if y is in S? All right, so this is just case 1. All right, let's look at that case. Can that happen? All right, 6. All right, so look at the definition of S. In order to be in S, we have to make sure that that element is not in the image of itself, right? So we know that the y is not in the image of itself, of y, right? So this comes from the definition of S, so that's number 3, and the fact that the y is in S, so I'm combining 3 and 5. All right, but interesting thing is that okay, so since f of y is exactly the same set as S, so we know that the 7 y cannot be in S, right? Which is a contradiction because look at line 5. Y is supposed to be in S. So, but y is in S, then it actually implies that y cannot be in S. So that's a contradiction. So this contradicts line 5. All right, but this came from combining line 4 and line 6. Right? So we got a contradiction. So we got in trouble in case 1. Right, so y cannot be in S. How about the other case? What if y is not in S? Right, so that's the second case. Y is not in S. Right, so this is case 2. Right, so if y is not in S, right, so in order to be in S, the element y has to be, I cannot be in the image of itself. Since y is not in S, it's got to be that the y is going to be in the image of itself. All right, so this comes from the definition 3 combined with line number 8. All right. But remember that the f of y from line 4, and we're going to combine with line 9, this guy is same set as S. So number 10, line 10, y is actually in S, right? Which is again a contradiction because remember that case 2 is y is not in S, so it's going to contradict line number 8, right? So therefore, either case, if y is in S, we got in trouble. Y is not in S, we got in trouble anyway. So which means that the assumption we made in the beginning was wrong. So 11, right? So therefore, we know that chi-naive of A cannot be the same as chi-naive of its own power set. Right, so this is by proof by contradiction. Right, oh, you can say rule over elimination or something like that. All right, so this proves that chi-naive of A is different from the chi-naive of its power set. All right, so combining 1 and 2. So 1, we show that coordinate of A is less than or equal to the coordinate of the power set. And but number two, we show that they're actually not numerically equivalent, right? Therefore, combining 1 and 2, so 1 and 2 tells you that coordinate of A is actually strictly less than the coordinate of its power set. Right? That's it. I hope that this was clear.